Hi everyone, we're going to finish up chapter 4 today. So we're doing 4.4 through 4.6. 4.4 contingency tables, joint and marginal probability. Well, a contingency table organizes data in two variables. So let me show you one of those so you know what I'm talking about. I've grabbed one we can paste in right here. There's a contingency table. In this contingency table, what they want us to do is they want to have us fill in the contingency table, any of the missing items, and they also want us to talk about what the joint and marginal probabilities are. So let's start off. They talk about the numbers inside this box. Those are called the cells. So this would have 6 cells. A cell is any of the number boxes that are not in the total, either the total column, the total row. Now, the rows go left to right. So we've got 3 rows, that's R1 through R3. We've got 2 columns. Columns go up and down, just like columns on a building. That's an easy way to remember that the columns are going up and down. And what we want to do, we want to fill these in. But in order to fill them in, we need to be able to look, and there has to either be a row with only one missing number or a column with only one missing number. Then we can go from there. For instance, that top row, I have 2 missing spots there. I can't figure out what they are, but in the second row I have the 2 and the 4, so I know those have to add up to 6. I'm just going to get the total there, and then I can keep going. The next row I can't do anything. The bottom row, the total row, I've got 2 numbers. One of them is an 8. They have to add up to 20. Well, so we know this one right here must be a 12. And so we just did a little math in our head. The 20 minus 8 was 12. And so we got that. And then now we can finish this one right here, because we know we've got the 3 and the 2, which is 5. They have to add up to 12. Well, that's going to have to be a 7. So what I did is I did the 12, and then I took away the 2, or the 3, took away the 2. So that's where that 7 came from. We can check real quick to make sure that column adds up to 12. So the 3 and the 2 is 5, and then the 7 is 12. So that one works. Similarly, the top one, we have a 4 and a 1, which is 5. They have to add up to 8. So that has to be a 3 as well. And then those add up across to 6. Down here in the third row, they add up to 8. And then we can check to verify 6 and 6 is 12, plus another 8 is 20. I know I've got the correct values in all of those boxes. Okay, so that's kind of how we would fill out a contingency table if they only give us a couple of things. We'll use the contingency tables. Oftentimes they're filled out for us and they're going to ask questions. Okay, so with this, let's talk about joint and marginal probabilities. Joint, if something's joint, it's combining things together. So if I look at one of these boxes, say one of these cells, say the 4, right here, since that's a combination of both R2 and C2, it's a joint. It's not a probability yet because it's just a value, but I could make it a probability. Remember with our F over N rule, by saying, oh, 4 out of 20, or 0.2, that would be the joint probability that R2 and C2 are both going to happen. So notice that that cell is an and statement. It's how often is it going to happen that R2 and C2 both happen? Well, it's 4 times, and it's 4 out of 20. So the probability is 0.2. Okay, so that's what the joint probabilities are. Any of those 6 values inside those cells can give us joint probabilities. A marginal probability is what we get as a total from either a row or a column. So if we take, for instance, this 8 down here, that's going to be a marginal. We can get the marginal probability from that. And that would be 8 out of 20, or 0.4. And so any of the totals in either a row or a column will give us a marginal probability. So what we're saying there is the chance that someone selected was in C2, well, that's going to be 0.4 as a probability or a chance of 40%. Okay, so that's that idea there. Let's do another picture. I'm going to pull up problem 411. Let me go grab that real quickly for you. So we'll go in here. Let me pull out my files, and we need 4111. All right, so we'll copy this in. We'll just go paste that in real quickly. Let's move that up. Okay, so here's another problem out of the book. It's talking about, as you can see, the New England Patriots, and it says from the National Football League website, in the New England Patriots roster, we obtained information on the weights and years of experience for the players on the team as of September 26, 2013. The following contingency table provides a cross-classification of those data. So we've got data on both years of experience and the player's weight. So they combine them, so each of those numbers inside the cells is a cross categorization of the years of experience and the weight of that player. So the first question says, how many cells are in the contingency table? Well, remember, the cells are just the one that have the raw data, not the totals. So we've got 1, 2, 3, 4 across the top, 3 going down, 4 times 3 is 12. So on A, we'll just say 12. 12 cells. Go ahead and write cells down. All right, how many players are on the New England Patriots roster as of September 26, 2013? Well, the number of players, that's going to be my total of the total of the rows, total of the columns. So on B, we would say 62 players. C says, how many players are rookies? Well, when we go to rookies, notice rookies right here. This column talks about rookies. So if we do a mark around that, well, the total number of rookies is 18. So we would just say that. Let me get those pictures out of there a little bit. Let's just say, here, look, it's this. It's just the total of that column. So for C, we'll go back to the blue pen, and there were 18 rookies. How many players weigh between 200 and 300 pounds? Well, between 200 and 300 pounds is this row right here. So we go to the end of that row and we say, oh, 40 players. I don't know why I said 40 instead of 41, but let's take that out of there. 41 players. I look back at that number, I said, that's not a 40. So let's go on to E. How many players are rookies who weigh between 200 and 300 pounds? Well, let's think about how we have to do this one. So we know this here. Let me get out this yellow highlighter. First of all, we know they're rookies. So we know they have to be in that row. Oops, that column. I just told you that was a column. And they weigh between 200 and 300 pounds. So they also have to be in this row. Oh, that was a much bigger spread. So where those two cross, obviously, is the number 11. And that would be the answer to that. So remember, that was a joint number. So that's an 11 is somebody that has to be in both of those. And so for E, we're just going to say 11 players. And so it's pretty easy to read these contingency tables. They're not bad at all. So what I'm going to do is I'm going to jump into the next section. Let's do this. How about this? Let's find that last probability, because we had talked about it before, just to make sure. So if I said here, probability that they're a rookie and between 200 and 300 pounds. Well, to find that, again, it's going to be the 11 that we had. We're just using F over N. 11 of those players out of the 62. And so then we could just do a quick calculation. Let me pull up my calculator. 11 divided by 62 and I get to 3 decimal places, 0.177. Okay, so that's the idea. Now let's jump into the next section, see what's going on there. So now we're in 4.5, conditional probability. Okay, with conditional probability, we add a condition on. So what that means is I have additional information. They write conditional probabilities this way. You're going to say the probability B/A. And that slash is pretty much straight up and down. And we read this as the probability of B given A. And what that means is that given A is more additional information. We know A has happened. Notice if you don't look at that B, let's cross that out real quick, or you don't look at the A, it just says probability of B. So the first one is always what we're finding the probability of. So I'm just finding the probability of A. I don't know why I said that again. We're just finding the probability of B, that's the first one. But now we've got this additional information that A has happened. Does that help us? Does that change the probability that B is going to happen? So that's the question it's asking. So let me give you a problem here and we can talk about these probabilities. So let me go and I'm going to grab problem 4130. So let me grab that real quick. This is just the next one. And we'll paste that in. Okay, so here's the problem. Now notice if you're looking in the book, if you're reading through the e-text or you have the physical book, 4130 is in blue, and it's not going to give you instructions necessarily right there, but right above it in the blue, it says in each of problems 4130 to 4133, we have presented either a contingency table or a joint probability distribution. In each case, determine both the probability of C1 given R2 and the probability of R2 given C1. Since that's in blue, when you get to problems 4, 131, 132, and 133, there's not going to be any instructions next to it. But since they're written as a blue number, that means the instructions, you have to look back until you get to a set of blue instructions. And that will be the instructions for those problems. Okay, so let's find these. Let's start off with the probability of C1 given R2. Now, here's what that means. That R2 is the additional information, additional info. In other words, we know R2 happened. What does that mean? That means we know that it's not anything in this table is possible, but it had to be R2. So if it had to be R2, we want to know the probability that C1 happens. Well, now we've narrowed it down. If C1 happened, it's only 8 out of 15. That's the chance that it's going to happen. So I'm going to put that in here. Again, we're just using F over N, but it's an 8 out of 15 chance, because if I know R2 happened, it could have only been one of those 15, and 8 of them were C1. So I just get that 8 out of 15. You can reduce that or not. Oftentimes they'll just leave it as a fraction. I'm just going to leave this one as a fraction and say that's our answer. Again, reduce the fraction if need be. And then let me erase these to go into our next problem. So now if I do the probability of R2 given C1, again, remember we're looking for the probability R2 happens, but we have that additional information that it was in column 1. So we know it's in column 1. Now pretend that's our whole table. And if that was our table and they said, what's the probability of R2? We'd say, oh, R2, 8 out of 11. And so that's what we do. Again, it's F over N, but it's just 8 out of 11. And so that's the idea. I'm going to erase these. No, I'll leave that there. We don't need to erase those right now. So anyway, that's the idea there. Let me give you a formula that they gave us in here. It's called the conditional probability rule. And it looks like this. Let me raise this up a little. I didn't need that. Go away. Okay, that's better. So the conditional probability rule. Sometimes we don't have the table, and so we need a formula, which they give us here. The conditional probability rule says the probability that B happens given that A happens is the probability that both A and B happen divided by the probability that A happened. And notice we didn't do all of those pieces, but when we go up here and we think of that in terms of that last problem, the probability of R2 given C1, the probability of R2 and C1, that was the 8 that I have circled in green. That was the probability of, well, not the probability, it was the number. It was that 8 was the number for R2 and C1. The probability of A on the bottom, remember that was the one that was the condition. Well, that was for the C1. That was all the C1s. So in this problem, here's what I'm saying. If we try to do this as the probability, now notice it's both of those, so we'd have to say R2 and C1 over the probability of the one that we know, C1, has happened. Well, if I do that, let's try to do that. The probability of R2 and C1, well, that's 8 is the number, but it's the probability, so it's 8 out of 25. And the bottom one, probability of C1, well, that would be 11 out of 25. And if you remember from your arithmetic, in order to divide fractions, my equals didn't look much like an equals, does it? Let's clean that up so I don't confuse anybody. You multiply by the reciprocal of the bottom one. Well, now the 25s divide, I get 8 out of 11, which is, of course, just what I had right there. So we see that works. That's how that formula works. Now, they do give a note on this, which, of course, since you've had algebra, probably you know this. You can never divide by 0. So the probability of A has to be greater than 0. And that's just a note there to make that an official formula. Okay, so we've got that. We could do that for any of those. I'm going to leave that there. But now what I want to do is I want to look at another problem out of the book. We're going to look at problem 134. So let me move this up so we have room, and I'll go grab it. 134. And as you see, we're kind of just zipping through these problems, which is nice. Hopefully you'll be zipping through these problems when you're doing your homework. Coin tossing. A balanced dime is tossed twice. The four possible equally likely outcomes are heads, 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 tails, tails, heads, tails, tails. Let A be the event that the first tosses heads, B the event the second tosses heads, and C the event at least one tosses heads. Determine the following probabilities and express your results in words. Compute the conditional probability directly. Do not use the conditional probability rule. So they don't want us to use that rule we just talked about. They just want us to find the probability. And directly, we're just using F over N. That's our basic fundamental property of finding probabilities. Okay, so the probability of B, if we do that, that says what's the probability the second toss is a heads? Well, if we look at what we have there, what's going to give us the second toss is a heads? Well, this one does, this one, the second one doesn't, the third one does, and the fourth one doesn't. So the probability the second one is a heads, well, 2 out of those 4. So I could just say, oh, that's 2 out of 4, or 0.5. And notice that should be true, because the chance that the second toss is heads, even if we don't know anything about the first toss, should be 1 out of 2, or 0.5. So let's see, let's go on to the, if they say put that in words, I would just say, you know, the probability is 0.5 that second toss is a heads. So I'm not going to put these in words. We'll say the words as we read the problem and talk about what it means. So now on B, probability of B given A. So let's say in words what it is. What's the probability that the second toss is a heads given that the first toss was a heads? All right, so let's do this. I'm going to erase these dots up here. We'll see which ones satisfy. Now, realize, what does it say? Given that A, probability B given A happened. So we know the first toss was a heads. So we know it either had to be this one or this one. Couldn't be any of the other ones. So right away, I know, oh, there's only two of them that could happen. And out of that, what's the probability of B? Well, B says the second toss is the heads. Well, out of these, the only one that's the second toss is the heads. Out of those two is that first one. We don't have to look at these because they didn't satisfy the condition of A, that the first toss was the heads. So it's just one out of those two. Again, that's going to be 0.5 as well. Part C says probability of B given C. Well, let's address this. What's the chance of B that the second toss is a heads if C at least one toss is a heads? All right, so let's erase these. Go back up here. So what do we know? We know C happened, so at least one toss is a heads. Well, this one has at least one heads, that has at least one heads, that has at least one heads. So there's three of them possible. Well, out of those three, we can cross that out if we want to. That helps. Out of those three, what's the probability that B happened? That the second toss is a heads. Well, that's going to be second toss is a heads. That's this one, and that's this one. Now it's 2 out of 3. If we want to round that to decimals, we could say 0.667. The next number, of course, after it's going to be 6 repeating, and since the next number after, it would be 0.6666. So we have to round up to a 7, or you could just again leave it as 2/3. Okay, so those A through C. Let me erase these, and then let's go back and we'll just see if we can do these all in a line. Probability of C. Well, what's the probability that you have at least one heads? Well, this time it's this one, or this one out of the total. So F over N, 3 out of 4. 0.75. E says, well, what's the chance, what's the probability at C if we know A happened? All right, well, that's going to change things a little bit. So if we know A happened, we know the first toss was a heads. All right, first toss was a heads, so it's either this one or this one. And if we say, well, what's the likelihood or probability that there's at least one heads? Well, if there's at least one heads, if the first toss was a heads, well, those both have to happen. Notice, out of those two, both of them have at least one heads. So it's 2 out of 2, which is 1, which remember that makes it a certain event. In other words, if somebody says to you, hey, I'm going to flip a coin twice, I want to know what the probability that at least one of these is a heads. And then they say, wait, before you answer, the first toss was a heads. You're going to say, well, if the first toss was a heads, I'm guaranteed that at least one of them is a head. That's why it's a certain event, because it has to happen. If the first one was a heads, at least one of them had to be. All right, let's go to F. That'll be our last one. I'll just put it over here so we don't have to scroll anymore. Probability of C if B did not happen. All right, so let's see. If B doesn't happen, B says the second toss is a heads. If B doesn't happen, let's do this real quick. If B doesn't happen, not B would be the second toss is not heads, or it has to be tails. So for not B, the second toss is the tails. Well, second toss is the tails, so it's one of those two. So given that, what's the probability of C? Well, what did C say? Yeah, then at least one is a heads. Out of those two, only the first one has at least one head. So it's 1 out of 2. And again, if we want to change that to a decimal, 0.5. And we're done. So practice these. I think the more you do, just like anything else, the more you will get the hang of it and it'll be quicker. And then when you get to the test, you'll be able to go through it real quickly and make sure you get the right answers. Okay, from there, let's go into this last section. Now, I'm going to tell you something before I flip there, because what we're talking about in that section is independence. That's one of the things we're talking about. But before we leave this problem, I'm going to show you something. If two events are independent, and I'll write this down in the next section as well. If, say, events A and B are independent, that means if one happens, it doesn't change the probability that the other happened. So if I look up here to A and B, notice the probability of B was 0.5. But on the second part, if I already knew A happened, the probability of B didn't change. Since those are the same, whether or not A happened, these are what we call independent. And again, you may be saying, what in the world are you talking about? Well, we'll see it more formally in the next section. Over here, I have different information. The probability of C happening is 0.75. But if I know A happened, that changes the probability of C to 1. Since it changed the probability, these are not independent. And so that's just kind of a little teaser for the next section, which we're going to go to right now. Okay, so 4.6, the multiplication rule and independence. So what we're going to do, let's go back. I really didn't want that blue pen. Let's go back to something we saw before. And when I say before, it wasn't very long before. It was the probability of B given A. Remember, we said, oh, that's the probability of A and B divided by the probability of A. Because remember, we know A happens, so that's going to cut it down to a certain probability. That's why the one that we know happens is on the bottom. Okay, so we start there. But if I do a little math from there and I multiply both sides of that equal sign by the probability of A, what I get is the probability of A and B, I'm changing the sides also, is the probability of A times the probability of B given A. And so that's a formula that we can find one of these if we have an A and B type of thing. We're trying to find a probability. So we have a formula right there. So let's do a problem and see how this multiplication rule works out. So let's go to 184. I'll grab that and post it. And as you can see, just one more problem after this. So put that in there, paste that in there. It says governors. The National Governors Association publishes data on U.S. governors and governors' political affiliations in terms of office. Based on that document, we obtained the following frequency distribution for U.S. governors as of 2013. There were 20 Democratic governors and 30 Republican governors. 2 U.S. governors are selected at random without replacement. That without replacement means the same governor can't be picked twice. So once that governor is picked, he or she is out of the pool. You have to pick somebody else as your second pick. A says find the probability that the first is a Republican and the second is a Democrat. Okay, so A, probability, let's write it this way. If the first is a Republican, say Republican first and a Democrat second. Well, watch what happens here. This really means if I use that formula we just had here, I'm not going to underline it. Well, obviously I'm going to underline it, but I'm going to take that away because I don't want you to think of that's divided by anything. So this chance, what I'm going to say, I can calculate this by saying, okay, it's the probability the first one's Republican times the probability that the second one's a Democrat given the first one was a Republican. And I'll show you how that comes out in this problem. So what's the probability the first one is a Republican? Well, that's going to be F over N, 30 out of all 50 of those governors. obviously that is 50. We have 50 states. Each state has a governor. Times the probability the second one's a Democrat being the first one's a Republican. Well, we still have 20 Democrat governors. But do we still have 50 governors? No, because we already picked one. So now there's only 49. So that's where that, given that the first was Republican, we took one of the Republican governors out of the pool. And so that's what we would have left. And we just multiply that 30 divided by 50 times 20 divided by 49. And I get 0.24, it's 48, so I have to round up to 245. And again, make sure if you're doing this in the computer, you round to the number of decimals they specify. Usually with probabilities, they'll go to 3 decimals. All right, let's try another one of these. Find the probability both are Republicans. Well, that's the first is Republican and the second is Republican. Well, probability the first is Republican times the probability the second is Republican given the first is Republican. Well, we already know that one's 30 out of 50. But now do we still have 30 Republican governors? No, because we can only, we select without replacement, we can only select that one once. So now there's only 29 Republicans left and there's only 49 total left. So that's going to change this, not a lot, obviously, but a little bit. Now, I don't know why I do know why I put 29. So we've got 30 divided by 50 times 29 divided by 49. Obviously, it's going to change it more because it wasn't picking another Democrat. We're picking another Republican, 0.355, round it off. C says draw a tree diagram. If you want to draw a tree diagram, I don't think I've assigned any tree diagrams, but what we would do here is we'd start off and we'd say, hey, the first one can either be Republican or Democrat. And then the second selection can either be Republican or Democrat. And if I picked a Democrat, the second one can either be Republican or Democrat. And what I can do, which is nice, is when I'm doing this, I can associate these probabilities. So if I picked a Republican first, that'd be 30 out of 50. If I pick another Republican, there's only 29 out of 49 left. That's the problem I just did. If I picked a Democrat next, there's still 20 Democrats and there's 49 people left. If I go to a Democrat, that's 20 out of 50. If I pick a Republican next, there's still 30 Republicans out of the 49. If I pick a Democrat, now there's only 19 remaining out of the 49. And then what's nice to find the probability of going Republican, Republican, for instance, I just multiply those together. So this would just be 30 out of 50 times 29 out of 49. That's what we did in that problem before. That was my 0.245, but I can find all the probabilities the same way. So if I go this path, for instance, then I'm just going to say, oh, that was 30 out of 50 times 20 out of 49. And then I can find the probability of picking a Republican than the Democrat. And you could do the same for the next two as well. I'm not going to. I will leave that for you if you want to do it. It's 0.245 also. Those cannot be the same answer. Let's see what I did. Oh, that's interesting. That was Republican first and Democrat second. I was just looking at the wrong number. So if I recalculate Republican, Republican, that should have been the 0.355. Oh boy. That wasn't my best work. This one would have been the 0.355. Sorry about that. If you multiply those out yourself, you had seen that, but we caught it, so we're good. All right, And then we could do the next two similarly, Democrat, Republican, Democrat, Democrat, and that would be our tree diagram. So anyway, that was C. Those help us find these probabilities. Okay. And then D, what's the probability the two governors selected have the same political affiliation? Well, that's going to be D, probability Republican and Republican, or probability, oh, let's not put that P there yet. Let's do this. Or Democrat 1 and Democrat 2. Now notice we have an or statement here. That's the addition rule. So that's the probability it's R1 and R2 plus the probability that it's D1 and D2. These are mutually exclusive, so we don't have to subtract away any commonality those have because there's no commonality. And so I can do those. We've got the Republican, that was the 0.355. The Democrat, I guess we'll do that. That's this path right here. We'll go Democrat. And so that one's going to be 20 out of 50 times 19 out of 49. We'll get that. Which is 0.155. And so here I'll put 0.155. Now, technically, you don't want to round to your very final answer. These are already rounded off numbers, so I'm not guaranteed that they're going to be accurate to 3 decimals. I'm only accurate to 2 decimals if I've only carried the intermediate steps to 3. But if I add those together, I'm going to get, let's see, 0.355 plus 0.155, 0.510. Now, I will tell you, had I gone before, let me go to 4 decimals, that R1 and R2, both Republicans, that 0.355. Oh, I lost that on here now. So let's see. That's 30 divided by 50 times 29 divided by 49 plus, and then we'll do the other one, 20 divided by 50 times 19 divided by 49. So I've done the whole thing there, and I get 0.5102, so it doesn't round up, so it was accurate there. But you have to be careful. If there's a final answer that you want, you shouldn't be rounding before you get to the final answer. So do be careful about that. Anyway, that's the end of that problem. What I did want to do is I want to state one more thing, going back to that idea that we said about independence, and then we'll do a problem. And so you can see what we're talking about. But B is independent of A. If the probability that B happens given A happened is just the probability of B. So independent. So the fact that A happened didn't change the probability that B was going to happen. So that's what that's saying. So look, there's the definition formula-wise, but let's say this, B is independent of A. If the occurrence of A does not change the probability that B happens. So there's a verbal definition rather than a formula for independent. Now, don't get independent confused with mutually exclusive. Students often mix those two up. They have really nothing to do with each other. Independent means one happening doesn't change the fact that the other is going to happen, or it's change the probability that it'll happen. Mutually exclusive means they both can't happen at the same time. Completely different ideas. So don't get those confused. But let me jump in. We'll do a problem so you can see how this works. So we'll do this last problem, 4185. And then I'll take that away. There it is. As you can see, it's a pretty large problem. We'll paste that in right here. There we go. So it's a big contingency table. It says medical school faculty. The Association of American Medical Colleges compiles data on medical school faculty and publishes the results in the AAMC faculty roster. The following contingency table cross-classifies medical school faculty by the characteristics gender and rank. So find P of R3. So on part A, we'll leave that there. On A, it says find the probability of R3. Well, what does R3 mean? Well, R3 means they're an associate professor. Well, the probability that they're an associate professor is F over N again. There's 40,379 of them out of the total of 98,993. And so the probability that if I just randomly select one of these doctors, one of these medical school faculty, the probability that they're an assistant professor, and I'll type this in, is 40,379 divided by 98,993, and I get rounded off, it's 4078, so I have to round to 408. Okay, B says, find the probability that there are three, or an assistant professor, given, now I have more information, given that they're G1. In other words, they're male. So again, we're doing F over N, but let's talk about this. Let me erase this. That's not an eraser. Let me erase this and this. All right, so here's what we know. We know G1. We know they're gender 1, which they have specified as male. So I don't look at the whole table this time. I just look at that column. Now they're saying, okay, if they're in that column, what's the chance that there are 3? Well, R3 being an assistant professor, that means there are 25,888 out of the total of 70,000. So now when I do F over N, those are the numbers that I'm putting in. We're saying, oh, if I know it's in G1, there's only 70,000 people in there. And out of those 25,888 were assistant professors. So now I divide those, 25,888 divided by 70,000, and I get point, it comes out this way. It's 3, 6, 9, 8, it's more stuff. But if I went around here, I look here, that's 5 or higher. So I round up, so the 9 goes to a 10, so the 69 goes to a 70. So this rounds off to 0.370. Erase that. But now look what happened. So C says, are G1 and R3 independent? No, they're not. Because the probability of R3 was 0.408. But if I know G1 happened, it changes the probability of R3, lowers it down to 0.370. So on part C, I'm going to say G1 and R3 are not independent. And we'll say because probability of R3 does not equal probability of R3 given G1. So I guess the answer to C would be no, and there's the explanation. So we'll put a big no right here and box that. No, they are not independent. Okay, so anyway, work on these things. I think you can get this. It just takes practice like anything else. So do your best, and we will meet back again here later, and we'll do some more